Continuing on with Unit 3, Topic 1, Gravity and Motion, we're now going to look at gravitational force and fields. The highlighted dot points there from the syllabus you can see. Now, when we're looking at gravity, we really need to sort of go back to the 4th century BC to sort of start this story, back in the time of Aristotle. He had this idea that the normal place, in inverted commas, for heavy objects was on the ground. So that's the reason why objects fell towards the ground, because that's where they naturally existed. He also identified there that he thought that heavier objects fell faster. Didn't necessarily do any experiments, but just sort of reasoned it through and thought about it, and that's what he came up with. It's then not until the early 1600s where that idea gets challenged by Galileo. He identified that falling objects actually fall at the same rate regardless of how heavy they are. So it doesn't matter what the mass of the object is, doesn't matter how heavy that object is, it's still going to fall at the same rate. So then late 1600s is when Newton comes on the scene and starts talking about gravity and coming up with a much better explanation for it. Basically the idea we're looking at here is that gravity is the force of attraction between any two masses. So when we're dealing with an object that has mass, any object that has mass, it is going to experience gravitational forces, and it doesn't really matter how big that mass is. If it's small, it can still experience gravitational forces. If it's large, it can experience gravitational forces. So there's the definition of gravity. The next thing then is that in order to quantify that force, Newton did a bit of work and discovered a mathematical relationship that described that force. So that relationship is known as Newton's law of gravitation, and we'll have a look at what that equation is and what the variables are. Now, as he developed this equation, he actually did it from observation and measurement. He didn't actually do it from theory as such. So this equation is one that we can use to predict forces, but it's not necessarily going to explain why those forces exist. So the wording that you need to be able to recall here is that the force between two point masses, and by point masses we mean masses that can be considered to be sort of concentrated at a point. We'll talk a little bit more about that once we've dealt with this equation in more detail. So the force between two point masses is directly proportional to the product of the masses. So that means that if either of the masses increases, then the force will also increase by the same scale factor. And we can express that in a form that's a little bit more familiar to you. So we could say that F is proportional to the two masses, so capital M and lowercase m, and then we can say that, so I'll just put that in brackets, and it's inversely proportional to the square of the distance between them. And if we write that as a proportional relationship, that would be F is proportional to 1 on R squared. So if R was to double, then F is going to decrease by a factor of 4. So the distance increasing means that the force is going to decrease by a fairly significant factor, or in fact the square of the change in the distance itself. Now if we combine those into an equation, F is equal to G capital M lowercase m over R squared. Now that is an equation that's in the data booklet, so I'm going to highlight that one. We'll talk about what those quantities are rather than just stating it, and we'll identify what each of those measurements mean and why we're using capitals and lowercase letters. So if we first of all think about it, we've got this situation then where we've got two masses. So we'll start off with that as our little diagram to represent this situation. So we know first of all that F is going to be the gravitational force in newtons. The next two quantities I want to look at are the capital M and the lowercase m. So I'm just going to list these out together. Basically, they're the masses of the two objects. Now, we're using the capital and lowercase because it'll help to make sense of the next bit of work that we'll do in the next video. But ultimately, we're just looking at two different masses. And they could be expressed differently. So in some sources, you might see that it's they list them as M1 and M2, but we're going to use capital M and lowercase m. So that would be, we'd have that as being mass M, and that would be lowercase m for the masses. Now R is the distance between the centers of mass. When we're talking center of mass, we're talking basically sort of the point in the object around which all of the mass of the object is concentrated. It's not something that we need to go into in lots of detail. We will have a quick look at it in class as to how you can figure out the center of mass. It's easy enough to do when you're talking about something as large as a planet that's very spherical in shape, given that the mass is fairly evenly distributed. So the center of mass of a sphere is basically just the center of the sphere itself. But if you're looking at irregularly shaped objects, that makes it a little bit harder to identify where the center of mass is. So like I say, we'll have a quick look at that. So that distance in this case is going to be between the centers of mass, so that would be that value there. Now the reason we use R and not S here to represent distance is because we could really have this object positioned at any distance R away from that larger mass. So that R basically becomes the radius of the circle, so I've sort of drawn part of a circle through here, so we could continue that all the way around, and any object that is that distance R away is going to experience the same magnitude of force. The last thing that we need to identify then is that value of capital G. Note that it's a capital, it's not the same as lowercase g, it's a different quantity. Lowercase g is the acceleration due to gravity, capital G is the universal gravitational constant. That has a very specific value that's determined experimentally, and the value of the universal gravitational constant is 6.67 by 10 to the negative 11 Newton meter squared per kilogram squared. Now you might look at those units and go, well, where do they come from? Ultimately they come from this equation. So we'll have a look at this in class as well. If we look at the variables that make up the rest of the right hand side, and the fact that we've got a force on the left hand side with newtons, we can then figure out what the units for G are, and it's a useful thing to be able to do in physics, to do a bit of a unit analysis to identify where those where the units come from and how different quantities have the units that they do. Now, just to make a few notes about this situation in a bit more detail, there are some important things that we should pay attention to. The first is that that force acts on both masses. So when we're looking at that diagram that we had above, the force that we're going to calculate there is actually going to exist on both of those masses. So we'd need to indicate that there's actually a force that mass is going to experience, and likewise there's a force that mass is going to experience. So both objects experience the force. So you can think of it as being that mass lowercase m applies a force to uppercase m, so that would be this one here, so it pulls it in towards little m, and then capital M exerts a force on little m and pulls little m in towards it as well. So both masses experience that force. If we then take that across to Newton's second law, so referring to Newton 2, we know fairly well by now that Newton's second law is about the force acting on a mass that causes it to accelerate. So an unbalanced force causes a mass to undergo an acceleration. So if we rearrange that, we can say that the acceleration is equal to the force divided by the mass. So we know that the force is the same magnitude on both of these objects. We can then identify the relationship between the acceleration and the mass. So force has the same magnitude on both masses, so the relationship then is that, fairly generally speaking, so a larger mass will experience a lower acceleration. So in that situation above, if we think of the larger mass, capital M, being significantly larger, it's going to experience a slower acceleration towards a smaller one. So while the forces are the same, the acceleration of this one would be smaller compared to this one. So that's fairly obvious if you think about your mass and the Earth's mass. You accelerate quite quickly towards the Earth, but the Earth accelerates very, very slowly towards you. So there is still that acceleration there, but it's negligible. The last thing to note about this force here as well is that the force is a vector, so it does have a direction, and it depends on which mass we're looking at. So force is a vector with a direction along the line of between the two centers of mass. So where we have the force calculated, we know that the direction of that force is along the line between the centers of mass. So that allows us to quantify the force more specifically in terms of its magnitude and its direction. The next important point to note from here is that all objects with mass experience gravitational force. So it doesn't matter how big or small they are, they're going to experience a gravitational force, and they can exert a gravitational force when they're near any other object with mass. So it doesn't matter how big or small, we can consider that objects with mass are going to experience gravitational force. In order to make that calculation a little bit easier though, we can identify this idea of point masses. So masses can be considered to be point masses. So what we mean by point mass is that you're kind of ignoring the size of the object and saying that all of the mass is concentrated at a single point. And there are two scenarios that we can simplify a mass to be considering it as a point mass. The first is if the object is spherical. So something like the Earth, given that it's fairly spherical in shape, we can treat it as a point mass. Likewise, if you look at any ball, the fact that they're very spherical, you could treat them as point masses as well. The second aspect to consider is the distance between the objects. So if that distance, or more specifically the distance between the centers of mass of the objects, if that distance is large enough, then we can consider that the objects are going to behave like their point masses. And what I mean by that sort of scenario is that if we consider, say, the Earth and you standing on the Earth, the fact that the Earth is spherical sort of fits that first scenario, so we can treat the Earth as a point mass. You standing on the surface of the Earth, the distance between the Earth's center of mass and your center of mass is significantly larger than your size. And so we can treat both you and the Earth as point masses, and so we can then apply Newton's law of gravitation. Next point is that value of g. So g is the constant of proportionality that links those quantities. So it's a value that is basically related to the mathematical relationship that we're dealing with, and usually it would be determined experimentally. So it's not actually a quantity that necessarily relates to theory. It's something that can be determined from experimentation. And so that value is a constant value. It's been tested a number of times and refined and found to be that value of 6.67 by 10 to the negative 11 Newton kilograms squared per meter squared. The last thing to note here is the equation itself is it can predict the forces, so we can use it to determine the force, it doesn't actually tell us anything about why that force exists. Even Newton identified this when he came up with this relationship. It doesn't explain why that force exists, it just quantifies it and gives us a value that we can use that helps to explain the motion of objects that are near each other when they're being attracted due to gravity. It wasn't until Einstein came along that he was able to identify what causes that force when he came up with his theory of general relativity. Let's now have a look at an example question. It'll be a fairly straightforward one. So we're going to calculate the gravitational force on a 70 kilogram person that's standing on Earth. So that's going to require a few pieces of information that we need. We've got the mass of the person, and we need some information about the Earth itself. And the information that we'll have there is the mass of the Earth being 5.97 by 10 to the 24 kilograms, and the radius of the Earth is 6.37 by 10 to the 6 meters. So this is now a situation where we're looking at, say, the Earth positioned here. We've got a person that's standing on the Earth, and we know that their mass is 70 kilograms, so we'll call that mass lowercase m. Mass of the Earth will be capital M, and then we need to know the distance between them, which is basically going to just be the radius of the Earth itself. So if we go through and solve this problem then, as I said, lowercase m is going to be 70 kilograms. Capital M is going to be the mass of the Earth, so that's 5.97 by 10 to the 24 kilograms. And the distance between them is basically just the radius of the Earth, because the height of the person is insignificant on the scale that we're talking about here. So that's 6.37 by 10 to the 6 meters. So the calculation then, fairly simple one, the force is equal to G mm on r squared, and so we can just substitute straight into that. 6.67 by 10 to the negative 11 is the value of G, multiplied by the mass of the Earth being 5.97 by 10 to the 24, and multiply that by the mass of the person being 70 kilograms, divided by the distance between the centres of mass being 6.37 by 10 to the 6. Now be careful here. It's a fairly common mistake to forget to do this squaring down the bottom here. And in some cases it might be that you forget to write it in. In other cases it might be that you write it in, but when you go to your calculator you forget to actually do that step, because ultimately you're typing in a lot of information for this value here. It's really easy to forget that squared, so just be aware of that one. Now when you do go through and calculate that, you'd find that that's 686.94 newtons, and given that we've got everything in 3 significant figures, we should round that to 687 newtons. So there's a quick question dealing with Newton's law of gravitation. We'll have a look at a few more of those sorts of problems in class, looking at maybe different planets or the force between you and the person sitting beside you, and make sure that we've got a good understanding of how that equation can be applied.